if you want to estimate the covariance matrix, so the assumption is that the rows are IID, right? They're coming from some multivariate distribution. I want to estimate the covariance matrix. Assuming the expectation is 0, then the covariance matrix would be this quantity. If the expectation is not 0, what you're going to estimate is basically just this quantity, which is second moment matrix. And then you can estimate the mean. And then if you have the second moment matrix and the mean vector, it's a very easy way, like, I'll let you think about it, how to like get an estimate of the covariance matrix. But this is the main component. This is the hard part of covariance estimation. The other term, which is like mean times mean transpose, that reduces the estimated mean of the distribution. So we're going to focus on this, and then a natural estimator, an unbiased estimator would be this quantity. And so we wanted to prove a concentration equality for this, which gives you a like a quantitative bound on the performance. So this was the result. The assumption is that the rows here are Subgaussian vectors. Okay. Let's see if anyone remembers what a Subgaussian vector means. So what was this assumption? Yeah.
Like if you take inner products with that vector with any other vector.
Yeah, okay. So if you take the inner product of this with any fixed vector, it would be a Subgaussian random variable. And then there was a particular way of defining the norm, which was basically taking the unit norm vectors, taking the inner products, and then looking at the norm of the resulting scalar. Here in this problem, this is from the high-dimensional statistics book. So in that book, I mean, that book usually uses this Subgaussian standard rather than the norm. So equivalently, so you can look at, take U, look at the inner product of xi and u, and look at the Subgaussian standard. And then in this problem, we're going to assume that these are going to be bounded by sigma squared for any u on the sphere. So this is saying that these, I mean, these are going to be the same because we're assuming things are IID. I actually forgot whether we need things to be IID. For now, I assume that things are IID. They're definitely independent. I believe we assume it to be IID. Otherwise, the mean is not going to be the right quantity. Okay, so and then we have this covariance matrix. I'm going to say covariance matrix, but really second moment matrix estimate. So that's this quantity, which is also equivalent to, so there are these two equivalent expressions, right? If you think about how the matrix multiplication works, if this is X, the design matrix, it's not hard to see that X transpose X over N can be written as the sum of these xi transpose, where basically xi transpose each row. So these are rank 1 matrices. And then the result is this. And so if you ignore the delta here, if you look at this part, roughly speaking, with high probability, what you're saying is that this is bounded by this times sigma squared, and sigma squared is sort of can be upper bounded by the operator norm of sigma. And so this is saying that this deviation is within this factor of the operator norm of sigma. So it's a relative error type bound. And so if you think about the case where this bound is useful, it's the case where n is less than d, sorry, d is less than n. And so this term is going to be dominant. And so you can further bound things by root d over n times the operator norm of sigma. And then if I want this to be less than epsilon, which will be a form of concentration, then I'll need n bigger than or equal to epsilon to negative 2 times d. So roughly speaking, you need of the order of d observations to estimate this within a given approximation error, let's say. And this is quite interesting because naively you would think maybe d squared is necessary, but that's not the case. Okay, yeah. Yeah, that's a good question. Whether this is optimal is certainly something that is worth thinking about. Whether there are other estimators, So this is the simplest estimator in this case. There are other estimators that I'm going to talk about in the context of the sparse version. But since we're not imposing any constraints, most of those other ones would basically reduce to this. Yeah, I'm going to talk about like variations of this that are interesting in the context of sparse problems. But the question of whether this is optimal, we don't have yet like tools to discuss this. I'm going to talk about optimality in hopefully towards the end in a sparse linear models, but not in this case. I'll leave it open, okay? But if you're interested, you can think about it, whether you can do better than this or not. I'm going to talk about you can do better than this if you assume more about sigma, but without any more assumptions. I'll leave it open for now. Any other questions? Okay, so let's try to prove this. What do you guys think we should do to prove this result? I started doing a few calculations last time. But I think before doing that, I want to manipulate this a little bit, put it in a format which is more so let's try. So these are the things that you'd observe in practice, or in some books. There is a slightly better way, I would say, of writing this, which is to move the complexity of the exponent into the bound. That would be easier in applications when you want to apply this result. One question is that how should I choose delta? This is very common. This is the kind of Subgaussian tail that you would get, and this result is suggesting that this is Subgaussian. This is good for that purpose. But in terms of the proof, sometimes it's easier to work with a different version. So what I'm going to do is like define this to be, let's say, t, right? Or if you want this whole thing to be t, right? And I'm going to try to invert this relation. It's going to be a little bit simpler. So how do we invert this function? Delta squared. I want to solve for t, sorry, for delta in terms of t. T is equal to C3 n times minimum delta and delta squared. Any ideas how to invert this function? So ignoring the C, it's something like when delta is small, which one is dominant? Dominant, delta would be dominant, or delta squared. Delta squared would be smaller. So okay, the minimum would be delta squared, right? Okay. So it would be this. And then after that, it would be, what would it look like? Maybe something like this, right? I'm going to ignore the c times, so just minimum delta and delta squared. So where do you think this is like, this would have gone up, right? So below 1, the quadratic is smaller. Above 1, the linear one is smaller. So this is the minimum of the two. So how do you invert this function graphically? What is the graph of the inverse? It's like calculus 1. It's like in high school. Sorry? Mirroring it against like 45 degrees. Yeah. So that would be the graph of the inverse function. So that would be like this. And yeah, so that basically would be. And there, this is mirrored itself, right? And you can see it's just it's like the maximum of the inverse of the two functions. So if you want to do this, you try to solve these two separately, these two branches. So this gives me delta is t over c3 over n. And then t is equal to c3n delta squared. This gives me delta is root t over c3 n. And then these are the inverses of the two branches. And then the result is that delta has to be the maximum. So that's the inverse function, if you like graphically think about it. Okay. And so if I do this, I can basically replace this delta with this expression, and my bound would look like this. What would it look like? Probability that sigma hat minus sigma op is bigger than C1 sigma squared root delta n plus d over n. And then I get plus, and then I'm going to, so this is bounded further by t over c3n plus root t over c3n. Okay. The price that you pay here is a factor of 2. So this is within a factor of 2 of this. So in terms of constants, you lose something, but it's a little bit easier to write. So you'd get something like this, right? And then I'm going to absorb these constants into another c prime 1. So that will be the result. Okay, this holds a probability e to the, there's some constant here, c2 e to the negative t. Okay, this is a little bit easier to work with and to prove. In practice, it's useful because let's say if I want this to be less than some like epsilon, then I just figure out what the whole bound is there. So I can then apply it to other sort of, if it's like an intermediate step in some argument, I know exactly what the bound looks like. Okay. So you're going to prove something like that. And sometimes you might see things like this, which is, again, I'll let you. So you might, in HDP book, you might see something like this, which is very close. So this is slightly better, but d plus t over n. It's another way of writing it. This part is definitely true. This one is an upper bound on this, so it's slightly better. But I'll let you like figure out whether we can write it this way as well by paying another price, like a little bit of a constant there. Okay, so far so good. So I'm going to prove this version. So how do we proceed in proving something like this? We did some calculations. Proof. Let's remember this little idea here. So we have, like, the first step is to just write something like this variational characterization. That's one approach to controlling the operator norm. That's the one that we have been using so far. So the operator norm of the difference is the supremum. Because it's a symmetric matrix, I can just look at these diagonal quadratic, like a quadratic form on the diagonal of it. This is a quadratic form. It's like U transpose. And the way you're writing is like U transpose sigma hat minus sigma U. And then U varies in SD minus 1. And then you can do a discretization argument. Okay, you do the discretization over the sphere. So N is an epsilon net of SD minus 1. And then what I would get is, it turns out I get like 1 over minus 2 epsilon because I have to discretize both these. I mean, just something like quadratic happens here. So just do it for yourself. And so if I take this to be 1/4, I would get a 1/2 here, right? So this would be less than or equal to 1/2. And so up to a factor of 1/2, I cannot control this. It's enough to control something like this. And we also know that the cardinality of this would be less than or equal to like 1 plus 2 over epsilon to the d, which is going to be bounded by 9 to the d, something like that. So it's exponential in d. Okay, so now I want to control. So problem reduces to controlling something like probability of sup u in n. Let's say u transpose sigma hat minus sigma u, let's say bigger than t. Okay. I'm going to ignore this. This just adds to the constant that we have here in the end. And because we're not keeping track of the exact constant, we can just ignore that. So it's enough to have similar bound for this. So what would be the next step? Just remind you what sigma is. Sigma is 1 over n, I from 1 to n, xi transpose, and sigma is just the expectation of any one of these. You're assuming they're IID. So, sorry. Yes, union bound. Union bound, let's do it at the end because at this point, it's just going to clutter, but that's the basic idea. So you union bound, but the problem then reduces to controlling one of these terms for a fixed u, right? So I need to, so by union bound, problem reduces to controlling this probability of u transpose sigma minus sigma u bigger than t for a fixed u in SD minus 1. Or actually in n, which is a subset of SD minus 1. So now what should we do for this? Let me write this down. So this would be sigma. So can we simplify this a little bit? U transpose 1 over n sigma I from 1 to n, xi transpose minus xi transpose, and then U how should we simplify this? Sorry? We're going to get there, but just for now, a little bit more simplification. Can I move the u's inside? Let me try that. I want to like multiply u's, right? Let's do this because this simplifies a little bit. So what I get is ui transpose xi transpose u, and then u also goes in, right? U transpose xi transpose u. So can I simplify this a little bit? Yeah, so this is going to be, for example, something like this squared, because xi transpose u and u transpose xi, they're the same basically. Not ui, u transpose xi. And this is the same quantity. Okay, this is the same thing. So what I would get is 1 over n, I from 1 to n, ui transpose, sorry, u transpose xi, u transpose xi squared minus the expectation of itself. So u transpose xi is a scalar random variable, and you're subtracting the mean, so this is a centered random variable. And then for different i's, they're independent. Right, so this is an average of independent centered random variables. This is a very nice, well-known object that we've been studying. So how do we get we can do Chernoff bound at this point, but we have done it already. Bernstein, yeah, so why Bernstein?
Because the inner products are Subgaussian, so their squares should be sub-exponential.
Great, yeah, so by assumption, u transpose xi, so u is an Sn minus 1, a d minus 1. So this is Subgaussian with parameter sigma squared, as we assumed, for each I. And then we know that the square of a Subgaussian random variable is sub-exponential. So this is like an average of a bunch of centered sub-exponential random variables. That's the Bernstein setting. So Bernstein inequality is very useful here. A generalized version, let's say Bernstein. So the only thing that we have to calculate is the sub-exponential norm of this. How do we calculate the sub-exponential norm? So we need u transpose xi squared minus the expectation. So this is the random variable. I want the sub-exponential norm. What can we do here? Triangle. Yeah, we can do triangle. Right, before doing that, what is the next inequality? Is less than or equal to? So let me do this. Up to constant, is this true? That's what you were saying. Why? The centering number, yes, great. Which we didn't talk about for the sub-exponential random variables, but it's true. It's basically a triangle inequality, as you point out. When you do the triangle inequality, the sub-exponential norm of this, because it's constant just itself, but then you can bound this by, it's just the second moment, and the second moment is bounded by another version of the sub-exponential norm. So you'd have to just recall that. This is like the, it's not actually a second moment, it's just the mean, right? It's the mean of the random variable. The mean is bounded by, you recall that if you have, if x is sub-exponential, let's say, then the pth norm is, anyone remembers how it would grow? There was like equivalent characterization of sub-exponential random variables. It would be psi1 norm times p. For the sub-Gaussian, it would be psi2 norm times root p. So the moments grow like root p for sub-Gaussians. For sub-exponential, it grew like p. So this is saying that x1, the L1 norm, this is the stochastic L1 basically. It would be like that. So this is just expectation of the absolute value of x. So this would be bounded by the psi1 norm. And so what we're doing here is just applying this to, so this is going to be our x, right? And so if you do the triangular inequality, that basically shows the centering level. It's like they're the same thing basically. Okay, so good. And then you were saying, what was the next step? Psi1 norm of square, if you recall. Yes, so this calculus that is in the HTT book is very useful. This is actually equal to the Subgaussian norm squared. And this by assumption is up to constants bounded by sigma squared. Right, this is by assumption. The Subgaussian sub-exponential norm, I mean, the sigma squared that we defined was basically up to constant, the same as this. So that this nice result. So now how do we write the Bernstein inequality? So these are like, think of this as yi, right? This is the expectation of yi. And so what I have is like maximum. Actually, let me do this. It's easier to do. The entire thing is yi. So what we have shown is yi, the psi1 norm, is at most up to constant sigma squared. Right. So if we call this k, you remember how the Bernstein would go, right? Anyone remembers? Bigger than t, less than 2, e to the negative some constants. What was the kind of min something here? Yes, good. Something like this, if you haven't done a mistake. Another way of doing this is this, if I recall, like replace. So Bernstein for sub-exponential variables. I mean, another way of doing it is yi, I'm going to replace t with kt, right? And this would just simplify this a little bit, min t squared and t. Okay. So in our case, I can just replace this guy with sigma squared. I get an upper bound because this is an upper bound on it. There is some constants to just absorb the constant into this. Okay, so there's this constant here, which is just conveniently, it's going to be here, but I can rescale t to just remove that constant and then push the constant to C. So I hope people are comfortable with that. Sounds good. So let's see. Yeah, let's do our own thing here. So what we have shown is the probability that, so recall this summation, this is just this guy, right? So the summation 1 over n summation I from 1 to n yi is that quantity over there. So what we have shown is U transpose sigma hat n minus sigma U bigger than sigma squared t is less than 2 e to negative c min t squared and t, right? Right. If you haven't done any mistakes, something like this should hold. Now I'm gonna do the, or maybe do like, we can do multiple things here. I can do the trick that I mentioned, simplify things a little bit. So do the invert this function, and I'm going to call it again. Maybe call it u. Let's call this u. So if I call this u, sorry, u. Okay, good. No, there's something else. What should we use? Sorry. Rho, yeah, so rho is a little bit tricky. Now let's do delta, right? So what would be the there's going to be another c, let's call this c1, sigma squared. If you invert it, it would be like, you can see like t would be root delta and then plus delta minus delta, something like that, okay? That's the trick that I mentioned here. So to invert something like this, you just invert each branch and then you take the maximum. The inverse of this would be like root delta, the inverse of this would be t, and then you take the maximum. Maximum is bounded by the sum, so it's a little bit simpler. So now do the union law. So probability max over u in the net, u transpose sigma hat n minus sigma, u bigger than c1 sigma squared root delta plus delta is less than what? How do we do union bound here? Cardinality of n times, there's a 2 here, e to the negative delta, right? And then this would be, what would it be? 2 9d e to the negative delta. Good. So we're almost done. So now what do we do? I'm going to kill this 9 to the d is exponential in d, right? How do I kill this? Sorry? Yeah, I can certainly do that. That's what you do. So e to the d log 9 minus delta, okay? So next what? What is it? Yeah, go ahead. I can definitely do, but I just realized that I'm missing something here. Can you see what I miss here? So if you look at this, there is something missing from this. N, yes. Where should I put the N? Yeah. So if you go back, the N should be here, right? What I wrote is for just the sum, but we were missing one important piece here, which is the N. So now if I invert it, what do I get? So it's like, you see, like I have, so when I try to invert this guy, right? Forget the C, I'm going to tell, like, sorry, set N equal to, delta equal to N min T squared delta. But each branch, when you set it, so delta is equal to NT squared, so I get T is delta over N root this, and then max basically these two. The T here, T over N. Delta over N. Right? And then this is bounded by root delta over N plus delta over N. So I just have to adjust this. So I get root delta over N here. C1 sigma squared root delta over N plus delta over N. Now this is good. So let's move it down there. So, okay, back to the business here. The rest should be fine. So how should we set delta now? So just an easy thing is to just take it as large as this to kill this, but a little bit bigger. For example, twice this would do, then I would get e to the negative something. What I usually do is, or people do here is, you still let some sort of parameter in the bound. So let's say, for example, I can take it to be 2 log 9 times d. That would definitely kill the first term. But I also let it, let's reuse t here. Okay, I add a bit of juice here to later if I want, I can use it. So if you do this, this bound would be like e to the negative 2, e to the negative, because I have a negative here, so I get, there's the log 9 times d minus 2 log 9 times d. I get log 9 times d, right, and then minus t, right? And then this is going to be, I can do like, this is less than 1. I'm just going to do it like that, okay? So this part is less than 1. Okay, it just remains to see what this part is. With that construction, I get this is going to be C1 sigma squared root 2 log 9 e plus t divided by n plus 2 log 9 e plus t over n, right? And then I can absorb this, the constants here, pull it out, put it inside the C. So this is, I'm going to write it, the full bound down here. So we get the probability that max u is in n, u transpose sigma hat n minus sigma, bigger than, let's say, C2, sigma squared root d plus t over n plus d plus t over n. It's less than e to the negative t. Okay. And this is actually the bound that we wanted to prove, actually the stronger version that I mentioned. We can do here. Okay, so this was the bound that I wanted to show. This is slightly stronger because root a plus b for positive numbers bounded by root a plus root b. So you can further bound this by this, you get this. So this was the one that we wanted to show. We showed something a little bit better, slightly better. Okay, so that's what you showed. This is equivalent to what we wanted to prove, even a little bit better. Okay, if you want, you can just rework out like the, this is further bounded, upper bounded by root d over n plus root t over n. I won't suggest doing this. I mean, this is already good. But if you want, you can do this, and then you can just transfer this back into this, you get a minimum. This is bounded by twice the maximum, and then you invert it. So you can move back and forth between this form of the bound and the form that has the minimum there, and just a t here. So this is sometimes what you see in the HDP book with some of the exercises. The form with the minimum usually is what you see in the HDS book. They're sort of equivalent up to constant. Okay, sounds good. So it wasn't difficult. It's just this idea of like moving it to back and forth. This is useful. This is like a trick. It takes a while to like appreciate it, but had we, I mean, if you go through my slides, the thing that I do here, I keep the minimum here, and then things become a little bit more tricky. But you can see once I move the complexity to this part, then it's really easy to figure out what delta should be here. Otherwise, I have delta and delta squared, then you have to worry a little bit how to choose the delta to cancel the d. But this just simplifies the argument. So any questions about that? So nothing super special here, except this trick that I mentioned. So the idea is very similar to the bound that we did for the just Subgaussian matrix with independent entries. We just reduce by discretization to the unit sphere and then individual sub-exponential bounds rather than sub-Gaussian bounds. Questions? Again, to recap, operator norm has this variational characterization. We discretize the sphere going to the epsilon net. We pay a price of 1/2. The size of the net is 9 to the d, exponential in d, which is expected. Then we control each one of these individual quadratic terms for a fixed u. Rewrite this, you get a summation here of centered, like an average basically of centered sub-exponential random variables. Apply centering, followed by the relation between psi1 and psi2 norm. We get a bound on the psi1, the sub-exponential norm, which is of the order of sigma squared. It's interesting, it's of the order of sigma squared because we get like things are squared here, right? So sub-Gaussian norm is of the order sigma, sub-exponential norm is of the order of sigma squared. And then you apply the Bernstein to these yi's. So you get this expression. Basically gives you the same bound for this quadratic form. You manipulate the exponent a little bit and then apply the union bound. You get the cardinality here. That will be 9 to the d. We have an exponential decay. We can cancel it by picking the delta correctly. And then the rest follows, okay? So you can see I can, for example, take t to be d, and this is the order. So you get like root d plus d, which is another constant. So this is saying basically that so conclusion is sigma hat minus sigma operating up to constant is sigma squared root d over n plus d over n with probability bigger than 2e, like 1 minus 2e to the like d, something like that, or whatever constant you want here. right? So if I do this, it's just going to be, so just take it to be like t to be c times d. So it would be something like that, or you could say it's just basically to e to the negative c1, it would be like d to the negative c1. So this is like a simpler form, just we just got rid of the t. So if d goes to infinity, this goes to 1, with high probability this holds. Okay. Questions? So this is our argument is very useful, and you can see it's just not very complicated, but very, it gives you a very nice non-trivial result about the operator norm performance of the sample covariance matrix, basically. Questions, comments? Okay, so then let's move on then, so you can follow the proof. It's actually harder, I guess. What we did was, this is the thing that I mentioned. Well, oh yeah, it's the other way around, in any case. Okay. Okay, this is something new. See what this is. Okay, so I'm talking about this. Maybe we should talk about this. Just I'm going to like briefly mention it. I probably don't want to talk about it. So there is this paper, Introduction to Non-Asymptotic Analysis of Random Matrices, by the author of the HTTP book. So it's an older manuscript, and it's also probably inside the HTTP book somewhere. What this is saying is you can. So what we did was to do operator norm of a Subgaussian random matrix, and also the second moment matrix of a design matrix with Subgaussian rows. Now suppose you have the design matrix itself, X, right? And then let's say the rows are X, XIT. So this is n by d. So what I can do, instead of like looking at X transpose X over n, I can ask what are the singular values of this? How do the singular values behave? If you recall how the singular values are sort of defined, the singular values of this are related to the eigenvalues of X transpose X, or vice versa, like even X transpose. So if n is bigger than d, X transpose X would be d by d. And so the singular values are related to eigenvalues, and it's not difficult to sort of see that because we have now a result on X transpose X, you can get the result on the singular values of X. So the kind of result that you have here is telling you if X has independent isotropic Subgaussian rows. Isotropic here means that like Xi X transpose is just identity. That sigma that we have is identity. So rows are independent, isotropic Subgaussian. So it's a special case of what we had before. Then for every t with this probability, we have this bound. So this is the maximum singular value of X. This is the minimum singular value of X. The maximum is bounded by this. the minimum is bounded by like below by that. So if n is much bigger than d, like this is bigger than, let's say, c, this part, then the singular value would be positive. So the matrix would be full rank, the smallest singular value with high probability. So this result can be recovered from the previous result by noting that it's just enough to show a bound like this. So for this, it's enough to show that the operator norm of 1 over nx transpose x minus identity is bounded by the maximum delta squared and delta, well, delta is this. So if something like this holds, then this holds, and then this basically is what we have shown. So let me see if I want to talk a bit about this. So so the thing is, let me so what we're saying is this guy is equivalent to this. Okay, and then this is saying something like so just let's look at this, for example. So this is the lemma. So if you have so we have something like this, A transpose A minus identity operator on the maximum of these two, then this implies this inequality, and then this implies that inequality. That's the lemma. So sort of this type of result is very close to this type of result up to constant. So if you want to show something like this, that the singular values of A are sandwiched between 1 minus delta and 1 plus delta, it's enough to show that, for example, this holds. Okay, and the way that this is proved is basically a very simple elementary identity. So if you set delta to be z minus 1, the absolute value, then this inequality holds. Think about this. This is just an arbitrary inequality. So if this holds, then if I apply this with z being this guy, the claim is that this follows. Why does that give me? So let's say I want to show A implies B. How do I use this inequality to show that? So if you look at this, this would be supremum, let's say maximum. X in, let's say, SD minus 1. X transpose A transpose A. Right? And this is going to be max. What would it be? Max X in SD minus 1. The AX squared minus what? Yes, which is 1 because x is on the sphere. Right, so the operator over this is basically deviation of ax squared minus 1. Ax norm squared to 1 over x. And so this inequality, what it's saying is, so S max A is just maximum AX x in ST minus 1. And S min, we can argue, is just the minimum AX x in ST minus 1, right? So what this is saying is, so this inequality is equivalent to just saying AX minus 1 in absolute value is less than or equal to delta for all x in ST minus 1. If you think about this, this is equivalent to saying that these quantities are between 1 minus delta and 1 plus delta for every x, and so the minimum and the maximum are exactly like sandwich. So that's this inequality, right? And then this inequality is this guy, so will be this less than or equal to max delta. That's the first part. A is saying this holds. Part B is saying the other thing holds. I'm sorry, let me do this. That's part B. And the part A is just saying ax squared minus 1 is less than or equal to max delta squared for all x and s d minus 1. And what we want to show is like A implies B. And if you compare these inequalities, it should be one of these. So this is saying so how should we apply this inequality to get A implies B? Any idea? I'm going to show that A implies B. There's a tree here. Yeah, the only difference is that this is squared here, right? The other one is not. So I can't see myself. Anyone can see the argument here? delta is z minus 1. Okay, I'll let you figure this out. There's something going on which I can't see. The inequality seems to go the other way. But the point is, this is something that we prove something like this is very close to something like this, which is the in terms of the singular value. So if you believe that inequality, if I want to show something like that, right, what this is saying is basically that if I divide by, let's think of the, if you want to prove something like this, you divide by 1 over root n, so you get 1 minus ck squared root t over n plus t over root n less than s min x over root n. Singular values are sort of linear in the sense, x over root n, and then 1 plus ck squared root d over n plus t. So if you think of this as delta, right, it's the same thing here. So in order to show that the singular values are between 1 minus delta and 1 plus delta, it's enough to show that this is less than max delta squared and delta. And this is the kind of thing that we showed. So I let you go. The argument that we did sort of shows this. And so from this, you can get something like that by this type of argument. So I'm not going to spend too much time on it. Just it's worth remembering that. So something like this, an expression that you can see here, some expression like this that we have proved, it tells you something about the singular values of x over root n as well. So you can translate that bound sort of easily. I'll let you work out the details to a bound of this form. Okay. Something like this you should be able to do. And then also think about this. Let me know if you found the way I wrote it, it might be not correct. I don't know. It seems correct, but it's a convoluted way of writing it. It's hard to see. Okay. Okay. I'm going to move on from this. Any questions? Just the point of this slide is that the same bound holds. We actually prove it for not necessarily isotropic case, non-isotropic case. So you can recover the results in this from that argument to some extent. Just do it for yourself. And then there's the non-isotropic case, which is the case of general sigma. And you can prove a bound basically. This is what we proved, sort of, and then this tells you something about the singular values as well, which I'm not gonna. Oh yeah, so there's, okay, so I think it's not exactly what we showed. The reason I included it is that, so this version is slightly different because what it does is working with the psi2 norm of the what? The whitened, basically. So when you apply sigma minus 1/2 to xi, you basically make it isotropic. If you go back to the previous result that we showed, it was just in terms of the psi2 norm of xi itself. This is in terms of the psi2 norm of the right-hand result. I think this is slightly different. So what you get, the k squared that we get here is this. Sometimes this is better. Other times the other one is better. So it's not exactly the same as the previous result, but it's proven by the same techniques. So something like this, you should be able to prove yourself. It's just that you can reduce the problem to the white-hand case and then apply this result. So in the white-hand case, the result is similar to what we proved. Yeah, I'm going to skip this because it will be a little bit confusing. Just know that these results exist and there are some variations on the result that we proved. Sometimes one of them is more applicable. Okay, I'm just going to move on from this. Let's move on to the structured covariance estimation. So that's where we want to talk about improved rates by adding more assumptions. So the simplest assumption that you can make is that the covariance matrix is diagonal, right? So if you assume that covariance matrix is diagonal, you just only need to estimate the diagonal entries. And this is an exercise you probably are going to assign. And then you can prove that you can improve the rate from root d over n to log d over n. This is not that surprising because, so if let's say sigma, this is not going to be sigma. So let's say if sigma was diagonal, how would you estimate it? Suppose sigma was sigma 1, 1, sigma 1, vector 2. So we know this. How should you estimate something like that? Yeah, it's effectively, let's say it would be like the diagonalization of sigma hat n. So the sample covariance matrix that you look at, you just look at the diagonal entries, which would be like the sample variances and then zero out the rest. So this expression that I have is not correct, but something like this is correct. If you do sigma hat, it's not going to work. But the point is that if I know the diagonal, I just don't need to estimate the rest. So what I would do is just diagonal, like restrict sigma hat to the diagonal, zero out everything else. And so the diagonal, like diagonalization is not a good term. But this estimator, which takes a diagonal sigma hat and zero out the rest, will have this rate. And this is not surprising because now these are both diagonal. What will be the operator norm of the difference in this case? What is a simple expression that I can write? Great. So that would be the maximum absolute value of the diagonal entries. Right. And you know that the maxima is related to the log d. So this is like the infinity norm of the diagonal entries. So it's not surprising that you get root log d. So this is a much better rate than this. So this is really high dimensional. But this is rather restrictive. But you can see how we can sort of extend it. Instead of assuming that everything is else is zero, we just assume that some of them are non-zero outside the diagonal, but the majority is zero. So that's the sparsity assumption. So if I have a sparsity assumption, meaning that sigma hat, so the population sigma is mostly zeros, the entries are mostly zero, then I could hope that I can get a log d type rate here. And so then you have to define what you mean by sparsity of an adjacency matrix. And usually what we do is just like coordinate-wise sparsity would do. The results that we're going to state are in terms of this, let's say, adjacency matrix of the sigma. So if you think of the sigma as, it's a symmetric matrix, you can think of it as the adjacency matrix of a weighted graph. I suppose I have something like that. And then the rest are zero. Okay, every symmetric matrix can be thought of as the adjacency matrix of a graph. So I have 1, 2, 3 here. So I'm going to put edges where sigma is, like sigma ij is non-zero. So you'd have like these self loops. And then 2 is connected to 3, but 1, 2, and 1, 3, the edge is not there. Okay, and then you can generalize this. So this, the adjacency matrix would be just like 1, 0, 0, 0, 0, 1, 1, 1. It's just puts 1 wherever these are non-zero. Okay, so that's the adjacency matrix. We're going to write it as A sigma. So this adjacency matrix is defined like this. And the thing is, the operator norm of this is a good measure of sparsity of A. So one example to see why this is an interesting measure, instead of counting how many zeros, that we can also definitely do. But if each row of this adjacency matrix has exactly S non-zero elements, then the operator norm of this is going to be bounded by S. And the reason for this is that there's this inequality, general inequality, that the operator norm of a matrix is bounded by root, this is like the interpolation inequality, infinity to infinity and 1, 1, and which is going to be just one of them if, so for symmetric matrices, is 1, 1, and infinity. Infinity operator norm and 1 operator norm are the same. So the operator norm of a symmetric matrix is bounded by the infinity, infinity, which is the max row sum. And so if there are at most S non-zero elements, the sum of the rows of the adjacency matrix would be at most S, so the operator would be bounded by S. But this sort of controls more complicated sparsity patterns. Yeah, let's come back and talk about that later. But we're going to come back and prove results in terms of the operator norm of this adjacency. Okay, thank you guys. See you next time. And